So, about class today, we're going to continue with the fast Fourier transform, very elegant, interesting algorithm that has many practical applications. First thing I want to do, though, is talk a little bit about the homework. I've received your anonymous feedback and so forth. One thing is I do hope you can start using Piazza to send me feedback so that I can respond to that feedback. I'm not aware of any method in Collab to create an anonymous conversation. And so when you say something, of course, I want to say, explain myself, or at least explain that I'm going to resolve that or take that into consideration. So the thing about the homework, I don't mean for this to be all-encompassing, take your entire life away. But I do want it to be a challenge to you. I don't want it to be like other homeworks where you just look at it and this is just going to take my time. I know how to do all of these things. It's just a matter of tediously writing these things. There has to be an element of challenge and of discovery in that homework. When that occurs, I think you actually learn the material more carefully. That said, my experience with people in office hours and so forth, you have to know the pattern of how I give homeworks. So these homeworks, all of the problems I give you, unless they're starred or marked by some sort of challenge, they are going to be closely related to algorithms that we have discovered or talked about in class. So the solutions will basically be of the same format of an algorithm that we've talked about in class. It may not seem like that when you look at the problem, but the solution is going to be a similar pattern. It's not going to be something very different. So when you approach a pattern, when you approach a problem, and your solution starts off with, first I'm going to handle this case, and then after that I'm going to do something like this for that other thing, and then I'm going to do something like that. This means you're probably not on the right track. The solution I'm looking for, and the simple solution that will be short to write and short to describe, will be something like, well, it's a divide and conquer problem. So first I will solve the left half, then the right half. Then I will do some linear time operation to put these two solutions together. Two of the problems in this week's homework are of that flavor. So your solution should be like that. Now that said, I would like to extend the deadline for the homework to Sunday afternoon. If that helps, I would like you to actually not feel so stressed. So, homework 2 extension. Remind everyone to complete the poll. Yes. So this is going to be part of your participation. I want to try to encourage you to participate. And so I've explained this in a post on the blog, but your participation grade is how I like in every other class, how do people measure participation? Some abstract notion of how you contributed to class. There's a nice way to record how you contribute by posting on Piazza either questions or answers. And there's also an anonymous way for you to get points, which is to have each of the polls that I give, which I will try to do once a week, to have 95% completion. So even if, it's easy, it takes 2 seconds of your time, and I get feedback from it. And it's one of those things where it's a common good. So the more people that respond, the better indication I get. And so that's why I want to encourage you to try to do that. Question? Oh, I know that nobody's giving up, because many of the experience I have is people are working in groups, which I really encourage. I think I bought pizza for one group that worked yesterday. I'm happy to do that for more people. I do think that you learn by explaining to people. There's an essay which I'm about to post by this German philosopher of 1905 on the origins of thought and speech. It was written in the style of 1905, so in order to say something that takes 2 pages, he's taken 107. So I'm trying to condense it. But the real point of this guy's essay is how great events in history happened because people had to talk about it. Like the French Revolution, he identifies a point in some guy's speech where he changed his mind and something else happened in the history of France. So this is the same sort of experience you'll have when you're solving these mathematical problems. As you're forced to explain them using your own voice, ideas will arise. Question. Question is, can you draw pictures and include them in your answers? And the answer is absolutely. That's why on homework 0, I had you basically produce a caricature of me, because sometimes a caricature of me might actually help in an answer of your homework. More importantly, if you draw pictures and draw diagrams and so forth, you can copy them and put them in your homework. Question. You can also put pictures of Jay-Z or Kanye or anybody else that you would want, or if you have any song requests or Spotify lists or YouTube playlists that you want me to play in class, you can also include that in your homework assignment, as long as it's exactly 2 pages. Fast Fourier transform, as I started in class last time, it's a very important algorithm. has many, many applications that don't seem to relate to how I'm going to present it. But at the core, the FFT is the heart of this thing. So take, for example, noisy data, or data that has a lot of like sensor data, or, for example, stock market data like Apple stock in the last few weeks. It goes up and down and up and down. You might want to say, I want to try to erase some of the random noise or the variation that's part of some unimportant fluctuation, and I want to try to smooth this data. Okay, so I want to produce, for example, like this blue chart right here. And the way that I'd like to do it is to take the natural standard way you do this is you take, so in this branch you take these 4 points and you somehow average those points. So you average every 5 or every 10 or every n data points, you put some smooth rolling average over all of that data, and that's how you create a smooth picture like this. For example, in digital pictures that you take with your camera, to get rid of noise, sometimes you try to apply a filter or a blur over certain patches of that image. All of these type of operations, at the heart of these operations, are fast Fourier transform, or convolution operations, and they're handled by the fast Fourier transform. Pattern matching. People who do work on genomics, when they have a huge 4 billion sequences of a monkey's DNA or your DNA, and you'd like to look for some particular type of gene or some gene that's expressed with don't care positions, where I want to match these guys, but I don't care about certain those positions. These fast string matching algorithms with don't cares are also handled with fast Fourier transform by way of convolutions. So there are many, of course, the iPad that you have, the iPod, any sort of music that you're playing, any sort of filtering that you're doing, digital filtering on that music, is also probably implemented with fast Fourier transform. Your phone, when it turns the signal of your voice into some digital stream, often one of the steps is take the fast Fourier transform of your speech, eliminate some of the high frequency noises, do something else, and so forth, and then turn it into digital packets. That process often also involves the fast Fourier transform. So it's a remarkable algorithm. As I said in last class, it was also very important for analyzing the sensor data, the seismic data that was used in order to make sure that nuclear weapons testing was compliant to the treaties that many of the superpowers had. How does this algorithm work? So the big idea is that we're going to change representations of mathematical objects. Some representations have efficiency benefits over others. Okay? So here we go. I'm going to give you a polynomial like this one right here. F of x is 5 plus 2x plus x squared. Now notice that the integers which define this polynomial, so if it's degree 2, then 3 numbers represent this polynomial. Those are these coefficients right here. Okay? So in general, if you have an n minus 1 degree polynomial, you have n coefficients. Now often one of the first things that you did in homework 1 is you take a polynomial and you graph that polynomial. So in this case, we can also graph this polynomial. For example, at x is equal to 0, then f of x is going to equal 5. And so we can graph that like this. And then when x is equal to 1, f of 1 is going to be 8. And similarly, f of 2 is going to be 13. So here is a better graph of this polynomial. As you can see, we have points like that, and so forth. Now the natural question is, if I give you just points, if I give you n points, do they define an n minus 1 degree polynomial? So I've just told you that if I give you n numbers, they can be interpreted as a polynomial, and obviously that polynomial I can plot at many points. What if I give you the opposite? I give you n points, like here I give you 3 points. Can you find a polynomial of degree 2 which interpolates those points? Yes? Everybody say yes? Yes, question? 3 different unique points. If I give you 3 unique points, can you interpolate a degree 2 polynomial between these points? Right? How would you do it? Yes? You can find something simpler. You can just solve a set of linear equations. Yeah. Exactly. Here we go. I'm going to skip right to it right here. So you get the first equation by saying, look, if f of 0 is equal to negative 5, here, let me write it up here. If f of 0 is equal to negative 5, then, so you know that your polynomial, you're looking for a, b, and c. Then what you know is that negative 5 is equal to a times 0 plus b times 0 plus c. And similarly, you have that 30 is equal to a times 5 squared plus b times 5 plus c. And you have this last equation as well. So now you have 3 equations and 3 unknowns. So you can solve this linear system for a, b, and c. So what have I just showed? I've showed that, at least in principle, I can use endpoints to represent a polynomial as coefficients, okay? Or I can use endpoints in the plane to represent a polynomial as well, because I can use interpolation in order to go back between those representations. So a polynomial has 2 representations. This is its coefficient form, okay? And if I give you, this is its pointwise representation. So polynomials have coefficient representations and pointwise representations, and that is what the FFT actually does, or the inverse FFT. It takes a polynomial in coefficient form and turns it into its pointwise form. And the inverse FFT takes its pointwise form and turns it into its coefficient representation. You will soon see, I promise, this is important, because what we're going to do is represent signals, like music signals or stock signals and so forth. We're going to represent them in their polynomial, in their coefficient representation. Okay? And when we want to manipulate them, we're going to turn them into their pointwise representations, manipulate them, do our stuff on them, and then turn them back into their coefficient representation. And it turns out that doing this is going to be faster than just doing brute force approach. Okay, so more formally, the input to an FFT is going to be n coefficients. So I'm going to put a really, really big red star, and I'm going to put some blue in there too, and also black. Okay? So because in the future, what I want you to remember from this class, when you are off in your jobs at Twitter, after their IPO and so forth, I want you to remember this slide. What does the FFT do? Even if you forget how it works, you should know what it does. As input, you get the n coefficients. As output, you are going to get the pointwise representation. You are going to get a of omega 0, a of omega 1, all the way to a of omega n, where omega n are distinct points, and they're specially chosen. That's all the FFT does. You can interpret, people interpret this, the FFT in math as a transform. In electrical engineering and signals processing, you have a different notion of what this is in sort of complex signals processing. And in computer science, we have our view of what the FFT is. They're all the same, but I think this is the simplest, most elegant one, of course. All it does, input, coefficient, output, pointwise representation. Now eventually, right, the same ideas that we use for the FFT, we're actually going to show that that same approach, in fact, the FFT itself, can be used as an inverse FFT. So in other words, the same technique and the same algorithm essentially, if you're given n points, okay, produce the n coefficients for the polynomial. Let me write it like this. So you're going to be given n points, w1, w0, w1. You are given n points, y0, y1, all the way to yn minus 1. And you need to produce the n coefficients for the polynomial a such that a of omega I is equal to yi. Now, we all know how to do this in brute force. The brute force way of giving a polynomial and producing a of omega 0 will take theta n operations. Right? You can compute a0 and then a1 times x and then a2 times x squared, etc. This you can do in theta n operations. And so, of course, the brute force way of computing a of omega 0 to a of omega n minus 1 takes theta n squared operations. And similarly, polynomial interpolation, by brute force, if you solve those n linear equations, if you do some Gaussian elimination and so forth, you can spend, if you do it really poorly, you can spend this much time, or you can spend, if you do it a little bit more cleverly, you can spend, of course, n squared times. You can do a lot of extra work that you need to. If you just do something poorly, you can take n cubed operations. If you do something slightly better, you can take n squared operations. But none of these are good enough for us. We are, of course, going to get an n log n solution to this. And that's what's going to make modern applications of mutes. For example, everybody knows this app called Shazam, right? What does Shazam do? Exactly. This algorithm, this application, this multi-billion-dollar business, Shazam, is made possible only by an algorithm like the Fourier transform, the fast Fourier transform. Okay. If it had to do n squared on these big songs, it just wouldn't be as fast. Not even feasible. Okay, so you know that the solution has this running time. So immediately, the first thing you should think is that, well, I know probably how the algorithm is going to work. It's probably going to follow a pattern like this. The pattern will be, I'm going to divide the problem into two equal parts, solve them, and then in linear time combine them. So you know that the solution has to have this form, and the solution will probably also take roughly 5 lines of pseudocode to describe. Do the left half, do the right half, and then 3 lines to describe how you combine the two. Okay, so here, I've drawn this because this is the heart of the algorithm. Should actually be a heart. Okay. So what am I going to do? I'm going to rewrite, this is the trick right here, this one slide. There's some flourish and some necessary components that come. This is the heart of it. I'm going to rewrite this polynomial like this. I'm going to just take the even terms. Everybody see what I did? I just rewrote them in 2 lines. Even terms on the top, odd terms on the bottom. Okay? And now what I'm actually going to do, I'm going to define a new polynomial called a even of x. And it's going to be a0 plus a2x. You can call it y if you want, just to make it clear. Okay. Once again, question? Yeah, so let's assume that n is a power of 2. There are ways to get around that, but in this situation, the simplest description, n is going to be a power of 2. So n minus 2 will be even, and n minus 1 will be odd. So I've written the even terms on the top. I then made a polynomial which reflects all of those even terms. And now this is the trick. All of a sudden, take a look at a of x. I can write a of x as ae of x squared plus x times a odd of x squared. That's the heart. First step. Why is a of x equal to ae of x squared? Well, notice when you evaluate ae of x squared, you basically get a0 plus a2x squared plus a4x to the 4th plus a6 x to the 6th, etc. Even this last term is going to be a n over 2 of x to the n over n minus 2. And similarly, when we evaluate a0 of x squared, we're going to get, and then multiply that by x, we're going to get a1x, which is this term, times a3x squared times x, which is a3x cubed, times a5 of x squared squared, which is x to the 4th times x, which will be a5 times x to the 5, etc., etc. So does this way of writing ax, is that clear to everybody? Okay. So now I want to make an observation, which is what is the degree of A0, of A even? Yes, both of these are degree n minus 2 over 2. So I started with the polynomial of degree n minus 1 sec, and I ended up with the two polynomials of degree n minus 2 over 2. Question in the back? No. Because we're actually going to get the extra x right here. So the first thing I did in this line right here is factor out an x. When I wrote A0, the first step I did is factor out an x and then do that. So now notice that AE and AO have essentially the same form. I'm just getting the odd powers with this external x right here. Yeah, so let me actually put this one up. It's probably easier for you to follow. Once you've understood this magical fact, the rest of the algorithm is going to fall out. So imagine recursively, I had already computed AE. Imagine recursively we had already computed AE on the points 4, 9, 16, and 25, and A odd on 4, 9, 16, and 25. What I would like you to do with your neighbors, partners, etc., compute A of 2 and A of negative 2, using only these numbers and the equations that are on the board. Okay. So I hear that many of actually, if you just substitute this into that blue equation, you see that A of 2 should be A even of 4, right? Because this is 2 squared, plus 2 times A odd of 4. And similarly, A minus 2 should be A even of 4 minus 2 times A odd of 4. And similarly, A3 is going to be AE of 9 plus 3 times A odd of 9, dot, dot, dot. And you can get to A5 and A negative 5. So, what this nice equation shows us is that if we can recursively, remember this is a polynomial of degree roughly half the size of the original. If we can recursively evaluate these two polynomials on 4 points, then we can use this equation right here and in order n time produce the evaluation of A on 8 points. And that is why that previous slide and this one are the heart of the algorithm. Because how are we going to evaluate AE and A odd on these 4 points? Recursively. How are we going to combine the results of this recursion with this equation? And so at a high level, you should now see that you can essentially evaluate any polynomial at n distinct points in order n log n. There's one more detail about how this works. Right? So let me actually just write the very high-level pseudocode here. So we will basically compute an array of evens right here by using the FFT on A even. We will compute the odds by running the FFT on A odd. And then we will return using the equation A of omega I is equal to A even of omega I squared plus omega I times A odd I squared. Now you can sort of see how this is t of size n over 2, this is t of n over 2, and this right here is going to be theta n, which gives us the algorithm. There's one remaining detail. The one detail that needs to be specified in order to fully specify the algorithm, and that is what points omega I do we use? And the reason this is an issue is, remember in the example, we had to have A odd and A even of 4, 9, 16, 25, 36. They had to be squares, right? And then the problem becomes to recursively, if you think about having a very big instance, right? the values that you need to have are squares, and then in the second layer of recursion, those values have to be squares as well. And then at the third level of recursion, those things have to be squares as well, right? So at every level of recursion, essentially the values that you're evaluating have to be squares. So using things like 4, 9, 16, and 25 are not going to work because the square root of 25 is 5, and the square root of 5 is going to be, again, some irrational number, something that's harder to compute with. It's feasible, but not very convenient. So that is the second part, the mathematical insight to the FFT algorithm. What we just talked about was the algorithmic insight, that we use divide and conquer. There's one other piece to this puzzle, which is figuring out the right set of points to use for this algorithm. And it turns out that there are several solutions to this. The one I'm going to present are the complex roots of unity. So when you have an equation like this, since this is a degree n polynomial, there should be n solutions to this equation. Those are called the roots of unity, the nth roots of unity. And those are well-known roots. So I'm going to try to identify the solution. I'm going to identify the solution to these equations. And the way I'm going to do that is to first remind you of this very nice equation. It is called Euler's identity. And I believe if you took APMA calculus, then you saw this equation, and you saw the derivation of how this comes to light. Question? I will possibly post a little simple explanation of the history of this thing. I think it's a really nice, beautiful thing. But for now, all I'm going to say is consider, if e to the 2 pi I is equal to 1, consider e to the 2 pi I j over n, where j goes from 0 to n minus 1. The first point I want to make is what happens when you take and you raise it to the nth power. What happens here? Well, essentially this becomes e to the 2 pi I over n times j to the nth. And of course, then you can move this n inside. And this part right here, you know to be 1. So this is 1 to the j, which is equal to 1. So by these 5 steps, we know that this right here, this is an nth root of unity. Okay? So there's only one other fact that's left. This is kind of a crazy number, e to the 2 pi I. What is this number? Is this a number? It's got an e in there, it's got a pi in there, it's got an I in there, a j and an n. The only real number in there is 2. Well, it turns out that e to the 2 pi I, again from calculus, is basically going to be cosine. This is from calculus. If you just take a Taylor series of this right here, and then factor the terms, you'll get the Taylor series for this and this. Aside from how this equation arises, the point is we now have a way to put a face to this number. It is actually this plus this. We know what a cosine is. We know what a 2 pi and a j and an n are. We know what a sine is. And so all we need to know is that this is a complex number, which is fine. Numbers, you can evaluate polynomials on complex numbers too. So just to be sure, I believe, okay, just to be sure, let's skip why it's true. Let's compute the first such root of unity. And then we have an equation right there. So we know that omega 1/8 is basically e to the 2 pi I. This right here is j, and this right here is n. So it's going to be 1 over 8. And if we plug those in there, this is going to be cosine of 2 pi over 8. Right, because the 1 over 8 there, plus I times sine of 2 pi over 8. And now, cosine of 2 pi over 8 is something that all of us are intimately familiar with. I've heard it. square root of 2 over 2, which I'm also going to write as 1 over square root of 2. Is everybody okay with that? Right, square root of 2 over 2, we can just write like this, if you multiply both sides by square root of 2. So this is, and the reason I want to do that is so that I can write this one like this. Okay? This calculation should make sense to you. I would now like to make you a little bit more familiar. So I would like you to compute all 8 of the complex roots of unity. Trust me, once you get the first 3 or 4, you'll figure out the rest of them. And a very convenient way of showing what these numbers are to graph them. So this right here is just, this is the imaginary, and this is, the real numbers. So you can basically graph them on such a plane, right? So omega 0 of 8, we've already done omega 1 of 8, right? Omega 1 of 8 was basically 1 over square root of 2 plus I over square root of 2. And so I'm going to try to approximate here. So that means that I go to 1 over square, let's say 1 is right over here. So then I'll do 1 over square root of 2, which is 1 over 0.7, somewhere here. And then I would say it's like right about there. This is also I. Okay, so this right here was omega 1 comma 8. On the handout, please, with your neighbors, try to graph the rest of them. Okay. So many of you have asked some interesting questions. First, what are the roots of unity? Well, if I were to describe them in words, they would be numbers that when you raise them to power n are going to be 1. So immediately, the 1 when raised to the power n is going to be 1. And similarly, negative 1, because n is going to be a power of 2 and so even, right? Negative 1 raised to the power n will also be 1. Now the other roots of unity are all going to be points that fall onto a circle. Right? So this is going to be omega 0 comma 8. This is omega 2 comma 8. Omega 3 comma 8. 4 comma 8. Did everybody roughly get that? And it's important for you at least once in your life to have evaluated these things. Once you do it once, you know that now all of the 16th roots of unity, they are going to be the points right here. And similarly, the 32nd roots of unity are going to be, and the 64th and the 128th, etc., etc. Now, the question was raised, why do we care about these roots of unity? What's so special about them? And that is essentially the point of the other side of your handout. It turns out, if you consider the 8th roots of unity, so this is n is equal to 8, and square them. So let's take omega 0, 8. If we square it, that's going to be 1 squared, and so that's going to be 1, which turns out to be omega 0, 4. Similarly, if we take omega 1, 8, which is equal to, if we square this, we're going to get did everybody follow my steps? When I squared this, I just FOILed it out. I get 1/2 plus 2 times I over 2. So this right here is I, plus I squared over 2, which since I squared is equal to negative 1, these two things are going to cancel out, leaving just I. So it turns out that omega 1, 8 squared is going to be omega 1 comma 4. And now you should verify to yourself, what is omega 2 comma 8 squared? So this is I squared, and that's going to be negative 1, which is omega 2 comma 4. There's a geometric interpretation of this type of thing. So if you look at this right here and you treat omega 1, 8 as essentially a rotation of 45 degrees, squaring that is equivalent to doing that twice. So if you rotate by 45 degrees and rotate another 45 degrees, then it's similar to have basically rotated 90 degrees, which is like this. And similarly here, if you rotate 90 degrees and you do that twice, you're going to come to this point. What about this point right here? When you multiply 135 degrees, and you do that again, what do you get? So let's confirm that. Let's do omega, I'll put this up. Omega 3, 8. Someone on this side that computed omega 3, 8, what was the value? A whole half of a class have computed these numbers. What is omega 3, 8? Somebody. Great. So now let's square that. So we should get 1/2. Sorry. This is a minus, right? And that is our correct interpretation. So this right here should come over to right there when we square it. So you can try to intuitively think that anytime I'm rotating in those chunks and I do it twice, I'm going to end up with a rotation that's either 0, 90, 180, or 270. And this is why we use these nth roots of unity, because squaring the nth roots of unity produce the set of n over 2th roots of unity. And that is what makes the algorithm possible. So let me come back over here. I'll put this one right here. So when we want to evaluate A at an nth root of unity, what we can do, what we need essentially is AE and A odd evaluated at the n over 2th roots of unity. And then we can use our same equation that we had before. And so this is what gives us a nice description of the FFT. An FFT is now basically going to be, it evaluates a degree n polynomial. This is what the FFT does. So again, I'm going to put the no black this time, because if you forget this one but still remember the first one, at least it's victory. So what the FFT is actually doing is we're evaluating a degree n polynomial on n distinct points. It just so happens that those distinct points are the nth roots of unity. And that's what makes this work. So what we're going to do is evaluate FFT on A even. This is going to produce the evaluation. We're going to do FFT of A odd, which will be, okay. And now, if we do A of omega I comma n, that's going to be omega I comma n times A odd, omega I comma n squared. But so notice that these points right here, for all I equals 0 to n minus 1, these squares will be n over 2th roots of unity. And so these recursive calls will have the answers. Okay? This recursive call produces the evaluation of AE on the n over 2th roots of unity, and since these are the n over 2th roots of unity, we can then combine the results of these two in order to get this. Does that, the puzzles all fit together? Are you in shock, or is it just disbelief as the elegance of how this all fits together? It doesn't make sense, or it's just amazing? No random coins involved in knowing the correctness of this one. So yes, you want to see it worked out. And what I generally do is I assign in homework the evaluation of the FFT on 4 points so that you work it out yourself. I will do one evaluation in class next week on Tuesday. I will go through the first few steps. But I do want to make sure that you go through the rest of the steps by yourself. What I want to spend the last 5 minutes of class on are just how this algorithm gets applied. Okay, so this is essentially the algorithm right here. And if I take it from your, your hilarious remark, there's both disbelief that all the pieces fit together like this and form Boeing 777 that actually flies. There's that disbelief that it all works. And there's also a little bit of confusion on exactly how the roots of unity, when you square them, become the n/2 roots of unity, etc. I'll try to address those with more examples. But please let this sink in, and please try to go over part of this lecture on the video and in the slides. Applications to multiplication. Remember, the best we had so far was this right here. We're actually now going to do much better, because the trick is to view this right here and this as a polynomial. So let's look at this essentially as a0 plus a1x plus a2x squared plus a3x cubed. And I'm going to make it a degree 7 polynomial. Just bear with me as to why. I'm just going to make the top coefficients 0. Okay? And now notice that, for example, a, when evaluated at 10, is going to be exactly this number, right? Because if each of these are base 10 digits, right, this will be 2, 0, 1, 4 as follows. Everybody see that? Okay? And similarly, I can write b as a polynomial Now, these are two polynomials. So what I can do to multiply these two numbers is I can compute the FFT of a, and that's going to get me a of omega 0 all the way to a of omega 7. I can compute the FFT of b. That'll get me b of omega 0 to b of omega 7. And now what I can do is just multiply these together pointwise. So I will get c of omega 0, which is basically the multiplication of a of omega 0 and b of omega 0. And I can continue doing that until I get c of omega 7. When you take this is why some representations of polynomials are better. If you want to multiply polynomials, the way we're going to do this in this algorithm, we're going to first evaluate the polynomial at twice as many points. So in this case, the degree was 3. It was 4 elements, so we're going to evaluate it at 8 points, both for a and for b. And then we're going to multiply each of those terms component-wise. So this step takes, this FFT takes order n log n. This one takes order n log n. This computation is going to take order n, but I'm going to put a little tilde there because there's a little bit of lying I'm going to do. And finally, what I'm going to do is an inverse FFT in order to do the opposite and turn this into, okay, and this one also takes order n log n. The idea is that pointwise multiplication of the point form representation of a polynomial gives you the point form representation of the product. So this c of x is equal to a of x times b of x. Okay? And now, of course, c of 10 is going to be a of 10 times b of 10, which is going to be the product. This algorithm, it was designed by Schoenhaage-Strassen, okay? And it takes, when you take all, this is Schoenhaage-Strassen, the same Strassen that came up with the matrix multiplication. And 20 years later, one of this guy's students, Martin Fourier, he had been working on this problem for 20 years. I met him the summer before he solved it, and then the summer after. And it was like I asked him how he came up with this. He said it's been culminating for 20 years. This guy, Martin Fourier, he has solved this algorithm in this amount of time. And this was in 2006. This is the fastest algorithm we know for multiplying numbers. This is a very small number. You can basically look at this number as 32. If log star is the number of times you have to take log in order to get to 2. So log star of 2 to the 65, 536, this is equal to 5. That's the point. Understanding the complexity of multiplying numbers, it's been a very basic question, and we've basically almost achieved an optimal one. So anyway, have a good weekend, and homework is due Sunday.